I'm not used to wearing a mic. I'm usually teaching. When I'm teaching, they don't give us mics, so I'm screaming. So pardon me if I scream at you. Where do I start here? I want to. This is a new initiative that I want to talk to you about. It has nothing to do with the traditional FSOSS that we have, or the traditional open source software stuff we do. It's something new that we started and it came out of left field. And I'd sort of like to describe to you what happened, what led up to this, just to start off. In the 1970s, I was in engineering, and I was interested in computers because I really didn't want to be an engineer. I wanted to do mathematical stuff in engineering, so mathematical stuff was computers and engineering. And I went in and I got interested in what was called the finite element method, which models continuous structures, okay? Whether they're airplanes or whether they're buildings or whether they're configurations of soil, it doesn't matter. Big structures in industry. And the problem we had then was that we had 256K of memory, and that was it. So we had to sit there and write code that would fit into this very limited amount of memory. And eventually, most people gave up doing computing in that area. I decided to go off to find another area that might be interested in computing, and that was soil mechanics. They were starting to model soils, move from back-of-the-envelope calculations to sophisticated computer calculations with soils. I went off to Cambridge University. They were interested in what I was bringing there, and we started something there. And by the time I finished at Cambridge, our main problem was that the mainframes that we were using, they took too much time to solve the problems, okay? These are real-world problems, and we just couldn't solve them unless we had an incredible amount of money. And we weren't going to get an incredible amount of money because all of the politicians had gone to the right, and they had decided education we have too much education, we can cut back 15%. So I went from one country to another country to another country, and I eventually ended up in the United States. And when I was there, I found work with a company that specializes in this kind of stuff throughout the United States, a company that was built around the flow of bulk solids, silos, corn sitting in silos, exploding, and all this kind of stuff. Again, big industry problems. What happened? We can't afford the computers that we need to solve this problem, so we're not going to bother doing the calculations. We're going to keep guessing. So that work stopped, okay? And then eventually I said, okay, what am I going to do? I've developed all this expertise. We can solve these problems, but the computational power is just too expensive. We need supercomputers, and we can't get the money for it, okay? Because only the big research institutes have access to this money. So I went into the field. That's the time when personal computers came on the scene, and lo and behold, if you wanted to do a scientific calculation, first thing you'd do is you'd buy a coprocessor. You'd take this coprocessor, you would put it put it on your motherboard, and now you could do a scientific calculation, a mathematical calculation, okay? This would cost $250 or something like that, right? And personal computers developed. Engineering companies, they would buy these to do their routine calculations, but nobody was doing anything really innovative. Meanwhile, the field that I had been in, I had been trying to work in and continue to work in, the finite element field, that was completely overtaken by supercomputers. And the only companies that could afford that were companies like BMW, Mercedes, people in the Hollywood entertainment industry, big money, okay? They would throw at it, you would throw money at these supercomputers, and they would solve these problems. You would have Meryl Streep's neck spinning around. All these things were possible, right? But if you wanted to do it on your desktop, you couldn't, okay? And then all of a sudden, in the late 90s, everybody, most of you in this audience, decided that the only thing you're interested in is playing a game. And you would want one game and another game and another game, and you would get a better computer, you would get a faster graphics card, and this would keep going, okay? This would keep going until what happened was that these graphics cards became as powerful as the computers that I needed to solve these problems. So, 2005, we came to a threshold where we could actually get this computing power onto our desktops because all of these people who are playing games, okay? And this is where this starts. This is where this starts. Let me get this slide here. Okay. This is where it starts, and it's called heterogeneous computing. Why heterogeneous computing? Because we take this 287, and we add it to a 186, or a 280. Sorry, we add it to a 286, and we got scientific computing. Then we had the Intel 386. We would add a coprocessor, 387, and then we eventually, in 1996. We have ATI producing a RAGE. I think I have one here. I'll pass it around. I'll actually pass all these around. You'll see this is a motherboard, okay? This is the first card you would buy. You'd probably spend about $150 for it. Then you'd go, your game is too slow. You'd buy this card. You'd plug them into a motherboard. If you just pass that around. You plug them into a motherboard, and away you go. And now your game, finally, your game it's still not looking very good, but now you can play it, right? And you get one step further. So, I keep thinking that I'm on a different computer. Better close this door. Okay. What happened here? What happened was very fundamental. We had a shift because of gaming. We had a paradigm shift, okay? Paradigm shift doesn't happen in software development very often. We had structured programming that threw out the assembly language programmers. We had object-oriented programming, which was an attempt to handle large problems, manage large problems using objects. And in 2005, we had what's been another turn, which is the turn towards concurrency, okay? What's concurrency? Concurrency is doing several things independently, okay? You do this independently and this and this and this. So you've got these processors. This one can do this and this can do this. They can do them independently, okay? And that's what we're in right now, okay? That's what we're in right now. Why are we in that? Why is, does this make any sense? This is an extremely important slide. What you've got here is you go along the bottom axis, you've got 1970 to 2010, okay? And the green line, the top green line, is the density of transistors that you can put onto a chip, okay? How many transistors you can put onto a chip. And we've been going along, and every 6 months, we double the number of transistors we can put on a chip, so we can get a more and more and more and more powerful CPU. The blue curve is the clock speed. The clock speed is how fast we can execute the instructions, okay? So you've got a bunch of instructions. How fast can you execute? And what's happened? It's leveled off. When did it level off? Just before 2005. We cannot we cannot get higher frequencies. We cannot execute instructions any faster, even though we can jam transistors onto a chip, okay? The blue curve is power. It's also leveling off at that time in 2005. What's happening? We need to execute that many instructions in that short a period of time. We need a lot of power. And if we put in more power, we're going to melt our chips. Okay? So we've hit a wall. We've hit a wall. We can't go further. So all this stuff about sitting there and everything is free and all you have to do is wait and you'll get more speed. All you have to do is wait another 6 months, you get a faster card, you get a faster CPU. That stopped. Okay? We can still increase the transistors, we can't increase the frequencies, we can't increase the power consumption. So this free lunch that we've had since the beginning is over. Okay? We now have to sit down and do some work instead of just waiting. Okay? Instead of just waiting, we have to work. And what kind of work do we have to do? We have to learn how to program differently. Okay? We have to learn how to program computers so that this unit, this computational unit, is doing something while this one's doing something. They're doing things concurrently. So the new phase, the new type of programming that you're going to see is programming that involves several computational devices. Okay? And the simplest, by far the simplest example is this. We have, nowadays, you've got a game. What do? You have a Core i7, which has 4 cores or 8 cores or whatever, and you have, let's say, for example, a GTX 580. And you put these two into your system, and what are they doing? Okay? What they're doing is the CPU is doing what it's always been designed to do. Take a whole bunch of instructions, very complicated, and manage them. Manage the communications with memory, do predictions on which instruction may execute, do that first, all kinds of sophisticated work for instructions one at a time in a serial fashion. What does the GPU do? The GPU, the graphics unit, what it does is what it's been designed to do. It's been designed to take pixels and just pump them to the screen 60 frames a second, okay? Because otherwise the gamers won't be happy. Nobody wants to wait, push a button, wait 3 minutes, and get a response. Nobody's going to play a game like that. Believe it or not, in the 1970s, when I would play a game on a computer, we would have to wait. But none of us have patience these days, okay? So if you look at the chip area, on a CPU, you're going to see that most of the area is devoted to cache, that's communication with memory, to the control unit, and just a bit is dedicated to the ALU, the arithmetic logic unit, where you execute specific instructions. With a GPU, it's completely different. What you have is you've got 480 or 580 or 1,000 cores that are ALUs that are executing instructions at the same time independently. And you've just got a little bit of room for registers and logic, okay? So they're designed to do different things. They're designed to do different things, each one to do its job properly. The GPU for parallel processing, so the same thing being done concurrently, and the CPU for what it always did was everything else. Okay? Everything else. Now, just some statistics here. Let's take a look at what we have as of, this is sort of this year, I guess. This slide goes up to this year. What we have on this side is we have performance gigaflops, which is billions of floating point operations per second, okay? We have a graph there, and along there we have the dates from 2001 down to 2012. The green line is the NVIDIA GeForce graphics cards. They're now up to 3,000 gigaflops per second, theoretical speed, okay? If you compare them to the Intel Sandy Bridge, if you look at the blue line, where it says Sandy Bridge, that's how fast an Intel core is, okay? It just can't perform. The CPU can't perform that fast, okay? And here's the most important thing on this slide, is the dark green one, the Tesla 2050, okay? The Tesla 2050 is a card that does computations, but double precision. Why is double precision important? When you're looking at a screen, single precision is enough. You don't care if this pixel is off by a little bit. You don't care about the accuracy. You've got six significant figures, that's good enough. When you're doing scientific calculations, you're doing predictions, and maybe some embankment may fail if you get the wrong, if you don't have enough significant digits, then you're going to be in real trouble. What you need is double precision. In fact, you need more than double precision. But all we have right now is double precision. It's starting to become available, okay? If you can compare the dark green Tesla with the gray line, that's Intel is the double precision gray line, Tesla is the double precision GPU, okay? The dark green line. So performance, we're starting to get to the point where scientific calculations can actually be done on these cards. We're just at the threshold, okay? We have a few years to wait, but it's a good time to start learning how to program these cards. And if you look at the websites, you see lists and lists and lists. We want this developer, we want this one, this one, this one, this one, who's programming graphics cards. Lots of jobs are starting to be advertised. Over here, we have bandwidth, okay? We have bandwidth, that's communications with data. Sandy Bridge Intel, the GTX 680. Huge difference in these cards, okay? They're very powerful. Now, what has the industry been doing in all this time? IBM, Sony, and Toshiba in 2001 formed an alliance called STI, okay? And they started working on the broadband cell processor. What they're doing is taking the CPU and the GPU, they're putting them together on the same die, okay? That's what they're doing. What about Intel? Intel, traditionally the producer of CPUs, okay, has a large share of the market. What are they doing? They've put their effort into what was called Mike, but they had to change the name to Xeon Phi because of some trademark disputes. They're putting the graphics processing and the CPU processing, again, on the same chip. AMD, Intel's competitor, what are they doing? They're creating what are called accelerated processing units, which are, again, the CPU and the GPU on the same die, okay? They're doing that. That's called fusion technology. Again, they had to change that. They had to change that because of a trademark dispute name. They've created a foundation called HSA, Heterogeneous System Architecture, and brought all these companies together. They're working with ARM and TI and all these companies to create an ecosystem where we're working, everybody is programming and developing hardware for heterogeneous computing. AMD took over ATI, okay? When they took over ATI, they got all of the Radeon graphics cards from ATI, okay? And they're still continuing that. So AMD has two strategies. One, combined CPU and GPU on the same chip, and discrete GPUs for gamers, because gamers need much more GPU power than these fused chips can provide. And on top of that, you've got NVIDIA. NVIDIA produced three types of technologies. One called GeForce, that's for the gamers, and that's where much of their income comes from. The other one is Quadro, which is for professional engineering applications, or graphics applications, but professional applications, so much more exact. And Tesla, which is the type of card for just straight computations. Here I have GTX 480, okay, produced by NVIDIA. Now, here's the share of the market that they have. AMD and NVIDIA have 99% of the discrete graphics market, okay? NVIDIA has 59% as of August, and AMD has 40%. Okay? Now the predictions, what's going to happen. This is what we have, okay? This is where the state of the art is. And now what are the predictions that are being made? Here's a slide which goes all the way to 2015, and this is a computer graphics market. And what we're concerned with is the part at the end. This part right here. There's an expectation. People are predicting that, professionals are predicting that from 2012 to 2015, we are going to have a spike, an increase in the market for science and entertainment, where we're going to be using low-cost graphics processor. What does that mean for you, primarily? It means that there's going to be a lot of jobs there where people want you to be able to program these cards. Now, I mentioned that Intel and AMD are fusing CPUs and GPUs. Okay, so what are the predictions for processors over the next few years? And what you have here is the maroon part of the graph is that refers to integrated graphics processors. That's the old technology where you would have an integrated chip. That's dying. The green part is the heterogeneous processing units, the stuff that AMD is doing. The discrete units is that broadband along the bottom. That's staying relatively constant, growing at the same rate of inflation that we have. And we have that new part, which is the embedded processing units. And why are those growing? That's the mobile market, okay? Try to play a 3D game on a mobile device, okay? You're going to have in your back pocket one of those cards. Good luck, okay? You won't find the battery power. So we have two distinct types of markets. Yes, mobile devices are a big thing nowadays, but graphics technology is, the discrete graphics part is still well alive, okay? So how do you learn to program these cards? Well, there are basically three languages that have been around that are good for this kind of programming. One is Fortran. That's the oldest one. That's what I used to work with until C and C++ took over. Now I know C and C++, and I've forgotten most of my Fortran. And what we have is we have Intel has developed extensions to C and C++ called Silk. They took work at MIT, and they simple extensions that you add to those languages, and now you can program those cards. OpenCL is a group, is now being pushed by AMD and HSA, the Heterogeneous System Architecture Foundation. CUDA is the C++ extensions developed by NVIDIA. And there's also Fortran 08, concurrent Fortran, and Fortran x86, which will allow you to run CUDA on an Intel chip. And there's direct compute by Microsoft. Okay? Now, who's teaching these things? There are three institutes teaching CUDA programming now in Ontario, as far as I know. One is McMaster. You've got to be in the master's degree program to do it. It's a special course in the master's degree program. Another one is U of T. Again, you have to be in a master's degree program to go into that course. And the third one is Seneca College. We're teaching that a full course. We have a full lab for that. And we started this semester, and we're going to be teaching that next semester also. We've filled up all the seats in the program, so we expect more students next semester. We have a 40-seat lab. We have 38 CUDA-enabled cards, enabled desktops where you can program them. You can go right now and you can run your games on there if you want, or you can learn how to program those desktops. Okay, it's T2108. We also have a Maximus workstation, which is, what's happening is that when you start to push these graphics cards so intensely, and they're doing two things, computations and displaying onto the screen, sometimes your screen vanishes because you're doing too many computations, okay? So you're at a threshold where computations and visualization are separating. And what we have is a workstation which will do the visualization separately and the computation separately. We also, of course, have access to SciNet, which is the supercomputer center out in Vaughan here, where you have a lot of these NVIDIA cards, and you can use as a test bed for programming. Okay, so this is what we have. On top of that, the students coming out of this course, they already have a solid background in C and C++. They're capable of programming, of profiling an application, finding out where the hotspots are, and focusing on that. They know how to move code from the CPU to the GPU, and they also know how to hide memory latency. The biggest problem with these graphics cards is you've got all this computing power, but to get the data, you've got to go out to Mississauga and come back, okay? So the processor is sitting idle there, and you've got to figure out ways to hide that latency. So you've got to have more calculations while you're waiting for the data to come back from Mississauga. We're also planning an advanced course in this, where the students can get more skills and learn how to interoperate with OpenGL and DirectX, and also learn a bit of Fortran programming. Okay. On top of that, so far, we have 4 faculty members who have specific interests in this area. We have Raymond, who is interested in intrusion detection. He's sitting right at the back there. Wave, Raymond. Okay. We have Peter Liu, who's interested in big data, geocomputation. We have Jordan Anastasiade, who's interested in cognition and computer tutors. If you've heard of Coursera, you know that the way things get marked nowadays in this new age of 1 professor and 10 million students is through robots. Well, we need computer tutors. We need automated tutors. All these things, these are coming on the horizon, okay? So he's interested in that area. I'm interested in the old area I was always interested in, which was finite element analysis, okay? So we have faculty who have specific interests. We also have a center we have CDOT, where you can find people who are interested in doing anything in these areas, not these specific things. So it's quite broad. Our interests are quite broad, and there's a lot of people who want to step in this area or on this threshold. We're not walking away just like that. Okay? Areas of application: image processing, manipulating images, MRIs, all this kind of thing, medical imaging, big data mining, gaming, advertising, genetics, quantum chemistry, molecular dynamics, mathematics, product design. You design a product, You're sitting there, you're designing, you make this change, right? The artist says, no, I want it to look this way. So you put the change and you see the result right away. You don't have to send it to a shop, come back in a week, and we'll discuss it again, okay? All this is changing. Scientific computing, that's the stuff I was talking about. Computational finance, so that's another area. There used to be companies that make predictions that work in finance. They have the markets close, and they've got until 10 o'clock the next morning to make their decisions, what they're going to invest in, what trades they're going to make. And in that period of time, they have to do all their calculations. Most of the software that they had before, they needed at least 12 hours to do the calculations. So the calculations would be out of date by the time market opened. Now, the speed up that they can get with these things, you have the possibility of making much better stock predictions, okay? And so I have before you, any of you who are interested in any of this research, I've got some pamphlets here, or if you know somebody who's interested in doing research in this area, I'd like you to pass these along to them if you can pass this. And if you know anybody who's interested in the specific research that I mentioned, be it big data or intrusion detection or anything, I have more precise descriptions here. So we're starting. We have a lot of momentum, a lot of initiative. We haven't done very much yet, okay? It's an interesting field to get involved in at the beginning. One of the fascinating things about it is everybody is a novice. Nobody has 20 years experience in this. So there's a shift in programming. I think it's a new area. Who knows? Maybe open source will start doing something in this area. We don't know, okay? Or they may stay in their traditional area, but it's something new, okay? Any questions? Any thoughts, ideas? Yeah? Why am I teaching CUDA over OpenCL? Excellent question. This was quite thought out, okay? There are two aspects. One, I got a bit of a push, okay? I got a push from NVIDIA. And two, as a teacher, my concern is at the end of a course, the students know the material that I've taught them. I can't just sort of say, well, I'm going to teach this, and if they don't learn it, that's their problem. I can't, okay? I'm a teacher. Okay? If I was a business person, it would be different, but as a teacher, I have to think about what is the easiest thing for my students to learn. And CUDA, by far, is much easier to learn than OpenCL. Okay? OpenCL is designed is platform independent, so it will work for any platform. It's very easy to move from CUDA to OpenCL. It's very difficult to learn OpenCL from scratch if you don't know anything about concurrent programming. So that's the decision, that's the pedagogical decision. Just a second. The pedagogical decision, okay? The push was simply marketing. NVIDIA markets CUDA. AMD hasn't got a clue about marketing. So AMD publishes a book on OpenCL. I open the book, and after page 3, I know my students will stop reading it. So what do? I tell my students to read the book, and they won't read it. The course will fail, okay? On top of that, NVIDIA gives us a whole lab of these cards. They set it up. They make us a teaching center. They want to push this technology. So we have collaboration with them, and it's the easiest thing to learn. I teach in the course, I teach CUDA, and then I show students how to move forward to OpenCL. So that's sort of the two-pronged answer. Yes? ATI was absorbed by AMD. ATI are not CUDA-enabled cards. You cannot use CUDA on ATI cards, but you can use OpenCL on ATI cards. On AMD cards, I should say, because they're, okay? You can use OpenCL on any of these cards, including NVIDIA cards. In fact, NVIDIA was the prime driver of OpenCL. Yes, yes, right, yeah, yeah.
That was where, you know, big money was going in.
Yeah, 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 yeah. Yes.
And then, 15 years ago, the distributed computing guys came along, and they proved that with distributed computing, they did things like SETI, the Human Genome Project,
Yeah, okay, yeah.
They said that handing out distributed computers to novice and the general public, we have a greater computing capacity than the blue genies.
Yeah.
So
yeah.
Where is the trend for research development, big, complicated
the only thing I can answer there is where is the trend. I went to an NVIDIA conference, okay? I went to an NVIDIA conference in May, and I'd say 60%, 60 if not 70% of the attendees are still from supercomputing, government money. So old projects that are there that are supporting the big supercomputers. 30% are the new people coming in, okay?
Are the supercomputing people looking at this, the GPUs and APUs versus?
Yes, of course they are. NVIDIA is competing with Intel to put the NVIDIA cards into supercomputers. And Intel, that's Intel's market. They want to keep that. So it's two different, what you have is two different ways of combining CPUs and GPUs, either discretely or on the same chip. For some applications, it'll work better the Intel way or the AMD way. In other applications, it'll work better the NVIDIA way. We don't know. And there's room for all those industries across the field. There's room for all those industries. But the important thing from our point of view, from the programmer's point of view, is we've got to learn, we've got to develop these skills if we want to remain marketable as programmers. And Seneca has to teach these things if we want our students to be able to get jobs or prime jobs in the marketplace. Yeah. Any other questions? Yeah.
Want to take on and adapt CUDA if they wanted to, or is it?
They don't. They're not interested.
NVIDIA allow them?
Will NVIDIA allow them? They would have to change their architecture. Because this is right down to the heart. This is the production of the chip, okay? And the closest we're coming to is that NVIDIA is cooperating with ARM, okay, to produce a system on a chip. The Tegra 4 will be CUDA enabled. Will have a CUDA enabled graphics processor. So I see more movement there than I see with AMD. I think AMD will slowly shift, will keep its Radeon cards for the gamers, but will shift to the heterogeneous system architecture that they've developed this foundation for. Yeah?
I just wanted to add one thing. NVIDIA does have support for OpenCL as well.
Yes, it does. Yes, yes. They've had it from the beginning. In fact, they spearheaded the OpenCL initiative. It's just that now it seems that they're not withdrawing from it, but their documentation is shrinking a bit.
And they're focusing more on CUDA.
Yeah.
I mean, like
It's an excellent product.
They control the hardware, so they can get all sorts of optimizations on it, right?
That's right. Yeah. Yes.
Professor, you gave a long history of your quest for high-speed processing.
Yes.
And during that same phase, 1970s onwards, I've been around at the same time. What happened to the quest for parallel processing?
It became special. It became specialized.
Becoming more powerful, more. Why couldn't
There wasn't a market for it.
No, but you're the professor, you've got the resources here to develop it.
I didn't have the resources to develop it. I was hitting the limit of the resources. That's why I had to stop my work. I was using Amdahl and CDC machines. I was using mainframes, and there wasn't enough.
No, but I'm saying the i386 processors.
Yes.
When they came to the 486 or
Yes.
whatever,
Yeah.
those chips are available cheaper by the dozen.
Yes.
One could develop a motherboard with 64 of them together.
Yes,
and
you
have a
could.
better
You could.
processor.
But it wasn't. It wouldn't survive in the marketplace. It wouldn't survive. The reason that we have this now is because of the gamers. There was a completely new segment that entered the marketplace. All these young people who are obsessed with games and will pump an incredible amount of money into gaming. It was a new sector, and that allowed the development, allowed all these companies to develop. And now we can use that, okay? Before, it would be, yes, 60 engineers, 70 engineers, 100 engineers. Who's going to finance the this development? Attempts were tried. You know, you would have this professor in this university and this one here and this one here. They would put their computers together. They would, take old computers and link them together. In fact, Raymond has a whole bunch in our office, right? Networked together. But we can't get it to the scale at the marketplace, okay? I cannot justify teaching, hundreds of students this technology, because where are they going to get jobs for it? Working for one professor? Yeah.
What's happening in the world of the shrink? We went from 130 nanometer down to 90, all the way down, and now we're at 0.018 or something. Isn't there a point where the shrink is, you just can't shrink anymore?
Yeah, there's quantum. Yeah.
You can't fire an electron.
Yeah, we have a quantum boundary. Yeah.
The gate's smaller than the actual electron. Where's the end of
I have absolutely no idea. I don't know anything about quantum computing. So you'll have to ask somebody else. I'm completely ignorant on that. Does anybody in the audience know? Yeah? Yeah.
One of the new materials now is graphene, and they're saying a 16th of an inch of graphene can hold 10 by 10 can hold an elephant, and there seem to be electrical properties of it would be the greatest to ever be used. It's going to be germanium, silicon, and graphene of all things.
I'm going to be retired by then. I won't be able to put two and two together.
Oh, you'll be around for a while yet.
Yeah, thank you.
I think there's also a Canadian company called D-Wave. You've probably heard of them. They have some experimental quantum computer which uses some sort of quantum annealing sort of method of solving problems, which is a weird form of concurrency.
But that's a different architecture.
Yeah, totally different physics.
That's what we have moved towards. We have those already. They're not very powerful. They're used by environments.
They're very
Quantum is not. We actually can't agree with one computer, but we've got generations of them.
When Intel was trying to tell us that we were going to get to 10 gigahertz, and there was the gigahertz myth happening, and gigahertz rules, and they weren't even talking about instructions per clock set. Then we got to a point where performance per watt was really important. Are we moving away from that now, or is power no issue?
No, power is. We're melting chip. We're going to melt chips. That's the problem. That's what I mentioned at the beginning there with this slide. Oh, let me bring up the slide here. Where are we? What have we got? Here we go. This one. F5.
Sir, is it the case that
go back.
Which number?
Oh, okay. Yeah. Pardon? You are some. I was absorbed with my slide here. I'm sorry. I missed the question completely.
Was it the case that as feature size was shrinking, that it was still allowing you to, the thermal dissipation was adequate, that, you weren't now pumping the chip, and because you can no longer shrink the feature size, the transistor size, that the heat problems are now caught up with you, that you thought that it's straining more the chips, or?
I don't know the technical answer to that. All I know is this thing heats up to 100 degrees centigrade, okay? The whole design is about dissipating the heat, okay? And that's this curve right here. The blue one, okay? We can't get any more performance, okay, without melting chips. So we have to. That's why you don't see single-core CPUs anymore, right? We went to 2-core, we went to quad-core, we have 8-core. If you're going to play a game, you're stuck. If you're going to do supercomputing, you're going to do this, okay? Yes? Can you speak louder? I can't hear you. Yes? Yes. There's a lot going on with that where you have the cards, or you have banks of these cards are in a remote location, and all you need is your laptop, and you come in and you have instant access to them. NVIDIA's doing a lot of work with Hollywood, with Lucasfilm, I think, on that. Yeah.